Hey guys, welcome back to the second video for chapter 6 where we're looking at the energy systems. Just thought we'd start off by doing a quick recap of what we looked at previously. So we looked at the food fuels, and so we looked at ATP, which was responsible for providing all energy for muscular contractions. Then we talked about how we had to resynthesize the ATP so we could have chemical fuels, which are ATP and PC, or we could look at using the food fuels, which was carbohydrates, fats, or proteins. And then last thing we looked at was the contribution of fuels and how fats were preferred at rest because we had lots of free oxygen. But then as our intensity increased and we need less and less oxygen supply, our carbohydrates then took over the dominant food for those times. So for this lesson, we're going to be mainly looking at this first key knowledge point on the side here, which is characteristics of the three energy systems, which we look at the ATP, PC, anaerobic glycolysis, and the aerobic energy systems. And we're going to look at seeing which physical activity they're involved with. And we're going to look at specifically the ATP rate, so how fast they're produced, and also the yield, how much they can produce, we've talked about already. And we'll also look at what fatigues and what limits the reason why they can't last and supply energies for as long. And also we'll look at the recovery rates associated with those and what's better, the active or passive recovery. So if we look at this diagram, we can see over here on the left, we've got three energy systems in total. Two of them are anaerobic. So anaerobic means they work without oxygen. So we've got two anaerobic energy systems that work without oxygen. That is the ATP-PC system and the anaerobic glycolysis system. And we've got one system which is aerobic, which means it uses oxygen. And that is quite simply the aerobic energy system. If we look through this flow diagram here, we can see at the top we need energy for physical activity, and we've already discussed how we can get that from ATP, and also how our fuels can help to resynthesize the ATP. So now what we're going to look at the second part of the solution is how can we use those fuels to resynthesize our ATP. So we're going to use our energy systems for this, and which energy system we're going to use will depend to do with our intensity and our duration. Okay, so a lot of the information you see here we'll go through later on, but essentially, again here we've got our two anaerobic, we've got our two anaerobic systems, our ATP-PC system and our anaerobic glycolysis system, and our one aerobic system, which is the aerobic energy system. We can see here it's a good summary. We've got our fuels. The fuels are responsible. What will cause fatigue in these systems, and also the best form of recovery. These are all things we'll go through as we go through each one individually. So the first concept you guys need to understand is energy system interplay. And essentially interplay is just talking about how the three energy systems work together to create the energy and provide the energy that we require. So a few key points. First one is that all three energy systems work together the whole time. So even after some of our fuels deplete, they're not fully depleted. There'll be a little bit of residual kind of contribution that will remain, but essentially all three will be there the whole time. We can see at the beginning, all three energy systems are activated at the start of exercise, but there will be one system that will remain dominant. So this word dominant just means which is providing the most energy at one point in time. The other two will continue providing, but not as much energy as the other one. Ways we can work out which energy system is dominant at a certain point in time is the intensity of the exercise, so how hard we're working, duration, which is the length. So I've got how hard, and we've got how long. And then some other things we need to consider is whether or not oxygen is present. If there's no oxygen present, therefore we're going to have to use one of those anaerobic energy systems which don't use oxygen. The other thing we might have to look at is also if there's been any chemical fuels or food fuels that have disappeared, we've been used up, they've been depleted. So for example, after 10 seconds of exercise at a high intensity, our PC stores will be depleted. There'll be very minimal left. So we won't be able to use those. So therefore, we probably can't use our ATP-PC energy system. This graph is looking at what might look like if someone was doing activity at submaximal intensity. We can see here The blue system is our ATP-PC system. So you can see contributes energy really fast, but it kind of slows down quickly. Our next one, this is an old terminology, so this would be known as our anaerobic glycolysis system. So that system will again peak really fast. So this is 25 seconds down the bottom. So within the first almost 10-15 seconds, it's almost peaking at its maximum power, and then it'll start to decrease again. We'll talk about what causes that fatigue later on. And we can see our aerobic system, after about between 45 to 60 seconds, depending on how fit someone is, it slowly increases. It starts at the very beginning, but its contribution is slowly increasing to a point where it becomes the main provider, and after 75 seconds it will always be that main provider. But we can see they're working together. Some terms we want to get used to. Dominant is meaning the energy system that's giving the most power at that one point in time. Predominant's talking about the energy system that gives the most amount of energy over a whole event. We'll talk about those a bit more in a second. The last two, rate. These are really good words to use when we're discussing and doing our responses in our questions. So rate talks about how fast we can supply energy, and it's kind of linked in with our intensity. So linked with intensity. And so ATP PC system, for example, can produce energy at the fastest rate, which means we can work at the highest intensity. Whereas the aerobic energy system, especially when we're breaking down fats, which is what lipolysis means, has the slowest rate, which means we have to work at the lowest intensity. As we discussed earlier, it needs lots of oxygen, so it's really slow. Yield means how much energy can be provided for that. We looked at that in the last lesson as well. We talked about the fact that carbohydrates, aerobically you can get 36 ATP from it. A triglyceride, you get 441 ATP from it. So we can see triglycerides have the largest yield. But if we think about, if we break apart a PC, we can only get 0.7. So we can see there as well, the yield from a PC molecule is very low. Whereas if we break apart down fats, we have the highest yield. Okay, now we're going to go through the three energy systems themselves. It'd be a good time to go OneNote now and open up each of those pages, which have the table for each of the energy systems. First one we're going through is an ATP PC system. And so to provide energy for this, what we need to do, we need to get the PC. To release energy from PC, we simply split that molecule. We're left with a Pi, we're left with a C, and also we're left with energy. So what we use this energy for is to complete that cycle we were talking about last lesson with the ATP, making ADP and PI, resynthesizing it back into ATP. So we can see up here on the top, we split apart PC, the energy we created here or here gets put back to put these two things back together. So ADP and PI will go back together, which gives us ATP. Once we've created ATP, we can go through the whole process again of breaking it down again. So we're left again with ADP and PI, and we can use that energy for movement. So that's the way it moves in a chemical base. Some things about ATP PC we need to know. Firstly, it's anaerobic, which means it doesn't use any oxygen, doesn't require oxygen, which is why it's a really fast rate. It's the most rapidly available source of ATP, and it's stored in the muscles and for simple reactions, so it's got a fast rate, as I said. For this system, it breaks down PC to resynthesize the ATP. Again, there's that word anaerobically, without oxygen. PC splits, we've talked about that. It then resynthesizes the ATP by joining the energy in here with the ATP and PI. ATP stores we've already talked about last for 2 to 3 seconds. Our PC stores, though, only last for about 10 seconds. So that means even though it's really fast, it's got a really high fast rate, it's got that low yield, and it also depletes. So PC depletes really quickly, which isn't ideal at all if you want to go for a long time. After 5 seconds, it's kind of when it's at its maximum intensity. Once our PC stores are depleted, it can be replenished, but it only replenishes when we do passive recovery. So passive recovery is simply sitting down, laying down, but pretty much really, really low intensity activities. The reason why we need to do passive recovery is because To restore PC, we need a lot of oxygen to put P and C back together. If you do 30 seconds of passive recovery, you'll get about 50% of your PC back. If you do 3 minutes, you'll get about 98% back. And after 10 minutes, you can't really see it, we get 100% back. So it is good. It comes back fast, but we need to do that passive recovery. Dominant, most power between that 1 to 5 second mark. And for any event that goes from 0 to 10 seconds, we'd say that ATP PC would have been the main provider of energy. Again, it's got the fastest rate, but it's got the lowest yield. It's got that. The problem is it doesn't last for very long. Typical events, they're short duration, and maximum intensity is the way we're going to think about that for ATP PC. Okay, so the next energy system we're going to look at is the anaerobic glycolysis system. And so anaerobic, meaning it still works without oxygen. So no oxygen, and glycolysis, meaning we're breaking down glycogen as our food fuel. So we can see we start here with glycogen, and then it becomes glucose. And at this point, we get enough energy from breaking apart glycogen to resynthesize 2 to 3 ATP. So it's still a pretty low yield. We're not getting that much ATP from it. That ATP we do create can be used for muscular contraction. But the problem is, because we're using it anaerobically without oxygen, when we get pyruvic acid, the next phase, we can't break it down fully. So we're only going to have a partially broken down molecule of glycogen. So with insufficient oxygen, our glycogen is going to turn into lactic acid. Lactic acid is often referred to as the bad guy. You might hear footy commentators talking about someone having high levels of lactic acid, but it's actually not the bad guy. What happens is lactic acid then gets broken down to two things, lactate and hydrogen ions. And they actually get produced at the same rate. So for every one lactate that's produced, hydrogen ions will also be produced. We'll come back to that a bit later on when we're talking about fatiguing factors. But in terms of anaerobic glycolysis system, how does it work? As we just talked about, glycogen is broken down without oxygen, so it's anaerobically broken down. It produces pyruvic acid, which is then converted into lactic acid because of the insufficient oxygen. A further byproduct of lactate and lactate is hydrogen ions, which makes the muscle acidity, muscle pH decrease, which makes the muscles more acidic, reducing glycolysis and causing muscular discomfort and the inability for the to contract maximally. My goodness, sorry, I can't speak anymore. So pretty much, as we talked about in the last slide, we have lactate and hydrogen ions being produced, and hydrogen ions are the ones that are going to be causing fatigue. So you can refer to hydrogen ions as H+ as well. So hydrogen ions will actually increase the acidity in the muscles, and will also cause it not to be able to maximally contract. Which, if you think about, if you're sprinting 400 meters, think about you turning this last bend in the 400 meters. Think about how your legs are feeling. Some people might describe it as feeling like jelly, and that's the accumulation of this metabolic byproduct, which is hydrogen ions. Hydrogen ions, that increased acidity, also prevents enzymes from breaking down glycogen as fast. If you've done biology, you might know that enzymes actually speed up reactions. So we're not able to have as fast reactions to breaking down glycogen, which means our rate will be decreased. It's pretty much a safety mechanism by our body to make sure we don't injure ourselves too much. In recovery, when we've got sufficient oxygen, our hydrogen ions are able to be combined back with the pyruvate and lactate, and they can be reconverted back into glycogen. So even in the short term, hydrogen ions are really bad. You might feel quite a bit of pain. You won't be able to have contract as forcefully. With an active recovery, where we're moving and there's lots of oxygen, so we've got high amounts of oxygen, we can actually buffer that hydrogen ions back to a usable source in glycogen. If we're looking at this, our anaerobic glycolysis system supplies energy at a slower rate than the ATP PC system, but because it's got more complex chemical reactions than just simply splitting apart the P and the C. The yield is twice that. So remember, PC had a yield of 0.7, whereas from this system, anaerobic glycolysis, we get 2 to 3 ATP every time we break down that glycogen molecule. It's dominant from the 5 to 60 second mark, and that can change depending on how aerobically fit someone is. The more fit someone is, this 60 seconds might even head down towards 30 seconds. And it's a predominant supplier, so the main supplier of energy for any event that lasts between 10 to 75 seconds. So if we look at all these events here, we've got the 200 and 400 meter sprint, 50 meter swim, and repeated sprint efforts in team sport. We can see they're all between this kind of duration, and they're all a fairly high intensity still. So remember, to work out which system's being used, we have to look at our duration and our intensity. Okay, so our third and final energy system is the aerobic energy system. And so it says aerobic, we're working with oxygen. We've got oxygen available. So our cardiovascular system and our respiratory system have worked up enough oxygen into the system to be able to break it down well. As we discussed early on, glycogen and carbohydrates is our preferred fuel to use. So you might see this stage here is exactly the same as the anaerobic glycolysis energy system, where glycogen went to glucose, we got the 2 to 3 ATP, and then we went to pyruvic acid. The difference in this situation with our aerobic energy system is that we have sufficient oxygen here, so we can go through a few extra phases. We can see here we go through something called the Krebs cycle. We go through something called the electron transport chain. You might have heard these kind of ideas about these two phases in different classes like biology. You might have gone through all the ins and outs of them. For this subject, PE, all you need to know is that it goes through the Krebs, it goes through the electron transport chain. You don't actually have to know what happens in there. The main thing to know, though, is that we get a total of an additional 36 ATP than compared to our additional 2 and 3 we had up there from our anaerobic way. When we go through this whole process, we're going to be left with 4 byproducts. The first one, we're going to have our ATP that we just talked about over here. We're going to be having some water, which is fine. We're going to have some carbon dioxide, which we just breathe out. We'll also have some heat, which by itself isn't fatiguing. However, if you don't manage your body core temperature, it can become a fatiguing factor. This is just another way of showing earlier on. We have anaerobic, so no oxygen, versus oxygen. We can see here down the bottom, we've got 3 byproducts which aren't really that fatiguing. Whereas if we don't have oxygen and we can't break down pyruvic acid properly, we end up with these fatiguing factors here, which we have to deal with. We're going to have to slow down. So how does this system work? We've talked about it a bit already, but requires oxygen. So we use oxygen. Carbohydrates is its preferred use, but we can also use our free fatty acids. So at those low intensity at rest, and for those really long endurance events, we'll be using our free fatty acids and triglycerides a lot more. When using carbohydrates, pyruvic acid is broken down through the Krebs and electron transport chain, and we're left with carbon dioxide, water, ATP, and also down here we're left with heat. This has the slowest rate, so we're going to be working at the lower intensities with these energy systems. Our yield is going to be the highest, so it's going to be 30 to 50 times. So remember, we had 36 when we break down glycogen, and we had 441 when we broke down triglycerides. Dominant and predominant for this one, pretty much remember, 75 plus seconds. Anything that's longer than 75 plus seconds is going to be aerobic dominant or predominant. So that's when our energy system will be providing the most amount of energy. There's no fatiguing byproducts. However, we'll discuss this later on. If we don't manage the heat properly, that will cause fatigue through dehydration and also another few things we'll talk about in the next area of study. Typical events, we want to think about long duration and sub-maximal intensity. They are the events that we can talk about when we're talking about the energy systems. Okay guys, so that's the 3 energy systems. I know there's a lot of information to take in, so I really encourage you to go back over the video, pause it, rewind, see what you need to go over again. Go onto Ed Rollo, which is down there in the in your homework on sector. Make sure you're going through things, ask questions. This is going to be a really good basis, and the energy system is something that we'll be going over and over again for the rest of this year pretty much. So it's really important you understand these concepts and you can apply them in different situations. Again, hope you're going well. Let us know if you need any help, and we'll catch you in the next video. See ya.